Welcome to this problem walkthrough. Today, we are tackling problem number 1945, titled Sum of Digits of String After Convert. In this problem, we will work through a string manipulation challenge that involves converting letters into their alphabetical positions and performing calculations on the resulting digits. Let's dive in. In this problem, we are given a string S consisting of lowercase English letters and an integer k. The goal is to transform the string into an integer by replacing each letter with its corresponding position in the alphabet. For example, A becomes 1, B becomes 2, and so on, up to Z, which becomes 26. Once the letters are converted, they are concatenated to form a single string of digits. After this, we repeatedly transform the resulting number by summing its digits. This digit sum transformation is performed exactly k times. After completing all transformations, we return the final integer value. The input constraints ensure that the length of S is between 1 and 100, and k is a small number ranging from 1 to 10. The output is a single integer, which is the result of these transformations. Let's understand this with an example. Suppose the input string S is I and k is 1. First, we convert each letter in S to its position in the alphabet. The letter I is the ninth letter, so the entire string I is transformed into 9999. Next, since k is 1, we perform one transformation by summing the digits of 9999. Adding these digits together, 9 plus 9 plus 9 plus 9 gives us 36. Since we only need one transformation, the result is 36. Here's another example to clarify further. If S is LeetCode and k is 2, we start by converting each letter to its alphabetic position. The letter L maps to 12, E to 5, E to 5 again, T to 20, C to 3, O to 15, D to 4, and E to 5. Concatenating these values gives us the integer string 12552031545. In the first transformation, we sum the digits of this string, 1 plus 2 plus 5 plus 5 plus 2 plus 0 plus 3 plus 1 plus 5 plus 4 plus 5, which equals 33. Since k is 2, we perform another transformation on 33 by summing its digits, 3 plus 3 equals 6. So, after two transformations, the final result is 6. Now, let's consider another example where S is Bax and k is 2. Converting the letters to their positions in the alphabet, Z becomes 26, B becomes 2, A becomes 1, and X becomes 24. Concatenating these values results in the string 262124. For the first transformation, we sum the digits of 262124, 2 plus 6 plus 2 plus 1 plus 2 plus 4, which gives 17. For the second transformation, we sum the digits of 17, 1 plus 7 equals 8. Since we've completed two transformations, the final result is 8. To summarize, the number of transformations depends on the value of k. If k is 1, we only sum the digits once. If k is greater than 1, we continue summing the digits iteratively until we've performed exactly k transformations. It's crucial to ensure that the string S is accurately converted into its alphabetic position values. Additionally, since the intermediate results can become large strings of digits, we need to handle these calculations efficiently to avoid performance issues. By carefully following these steps, we can compute the desired result for any valid input. To tackle this problem, the first step is to understand what it requires us to do. We are given a string S consisting of lowercase English letters, and we need to convert it into a numeric representation by replacing each letter with its position in the alphabet, such that A becomes 1, B becomes 2, and so on. Once we have this numeric representation, we repeatedly sum the digits of that number 4k iterations to arrive at the final result. A straightforward way to approach this is through a brute force method. Here, we manually map each character in the string to its numeric value and concatenate these values to form one large number. Then, for k iterations, we sum the digits of this large number. While this approach is intuitive, it has some drawbacks. Concatenating characters into a large number is inefficient, and repeatedly summing digits of such a number can become computationally expensive, especially as the number grows large. The time complexity involves O(n) for the initial conversion of the string and O, k*m, for summing the digits, where m represents the number of digits at each step. The space complexity is also O(n), since we need to store the converted string. Overall, while this method works, it is not the most efficient solution. A more efficient approach builds on some key observations. Instead of forming a single large number from the concatenated values, we can directly compute the total sum of the numeric values of the characters in the string. This eliminates the need to handle large intermediate numbers. After calculating this initial sum, we can then repeatedly sum the digits of this result 4k steps using a helper function. The Python implementation of this optimized approach is straightforward. First, we calculate the total by summing the numeric values of the characters in the string. Each character's numeric value is derived using the formula ord, ord, plus 1. Once we have this total, we repeatedly sum its digits 4k steps. This is done by converting the total to a string, iterating over each digit, and summing them as integers. The process continues until we complete the k iterations. This approach is not only simpler to implement but also much more efficient. The time complexity involves O, n, for computing the initial sum and O, k asterisk log, total, for summing the digits, where log, total, represents the number of digits in the total. The space complexity is reduced to O, 1, as no additional space is needed beyond the variables used. By avoiding the formation of large numbers, this method is both faster and more memory efficient. The brute force approach, while easy to understand, is not practical for larger inputs because it involves creating and processing large intermediate numbers. The optimized approach, on the other hand, eliminates these inefficiencies by directly summing the numeric values and iteratively summing digits without forming large numbers. This makes it not only faster but also better suited for handling larger inputs. However, there are some trade-offs. The brute force approach is more straightforward and intuitive, while the optimized solution introduces some additional logic to improve efficiency. Despite this, the optimized method remains simple to implement and avoids potential numerical overflow issues that could arise in other methods. In conclusion, the optimized approach strikes a good balance between clarity and efficiency. By leveraging key observations about digit summation and avoiding unnecessary intermediate steps, it is well suited for competitive programming scenarios where performance is a critical factor. In this problem, we are given a string s containing lowercase English letters, and our goal is to convert it into an integer by replacing each letter with its corresponding position in the alphabet. For example, A becomes 1, B becomes 2, and so on up to Z, which maps to 26. Once we have this integer, we repeatedly sum its digits 4k iterations to arrive at the final result. To achieve this, we begin with the first step, converting each letter in the string to its alphabetical position. This can be done by utilizing the ASCII value of each character and applying the formula ord, char, ord, plus 1. For example, if the input string is ABC, the positions of the letters at B and C are 1, 2, and 3 respectively, resulting in the sequence 1, 2, 3 as our intermediate output for this step. After we have the numerical positions of the letters, the next step is to concatenate these values into a single string. This makes it easier to work with the entire number as one large integer rather than a list of separate elements. For instance, if the positions are 1, 2, 3, concatenating them produces the string 123. With this string representation, we can now proceed to calculate the initial sum of its digits. To do this, we iterate through each character in the string, convert it to an integer, and add it to a cumulative sum. For example, with the string 123, the sum of its digits is 1 plus 2 plus 3, which equals 6. This gives us the initial digit sum that will serve as the starting point for the next set of operations. Once we have the initial digit sum, we proceed to repeatedly sum the digits 4k iterations. If k is 0, we simply return the initial digit sum, as no further operations are needed. Otherwise, at each iteration, we convert the current number into a string, extract its digits, and compute their sum. This process continues for k iterations or until the number becomes a single digit, whichever comes first. Notably, if the number reduces to a single digit during the process, we can terminate early since further summation would yield the same result. For example, if the initial sum is 123 and k is 2, the first iteration gives 1 plus 2 plus 3 equals 6, and the second iteration confirms that the number is already a single digit, so no additional computation is required. The final output in this case is 6. There are a few key insights that help optimize this algorithm. First, mapping letters to their alphabetical positions using ASCII values is efficient, with a time complexity of O(n), where n is the length of the string. Second, the digit summation process benefits from the fact that the number of digits decreases significantly with each iteration, making the summation increasingly faster. This ensures that even for large numbers, the process quickly converges to a single-digit result. Finally, the early termination condition adds an additional layer of efficiency, as it avoids unnecessary computations if the number reaches a single digit before completing all k iterations. To implement this algorithm effectively, we use three main data structures. First, an array is used to store the integer positions of the letters in the string, enabling efficient processing of the input. Second, a string representation of the concatenated numbers simplifies the digit summation process, as we can directly access each digit as a character. Finally, an integer variable is used to track the cumulative sum of digits during the iterations. These structures together ensure that the algorithm is both efficient and easy to implement. The complexity analysis of the algorithm provides valuable insights. For time complexity, converting letters to their integer positions requires O(n) time, where n is the length of the string. The digit summation process depends on the number of digits d in the initial sum and the number of iterations k, leading to a complexity of O(d*k). Combining these, the overall time complexity is O(n plus d*k). For space complexity, storing the alphabet positions in the concatenated string each requires O(n) space, resulting in an overall space complexity of O(n). We must also consider edge cases, such as an empty string where the result is immediately 0, a single letter which simplifies computation, and scenarios with large k, where early termination ensures efficiency. Additionally, strings with repeated letters are handled seamlessly due to the linear processing of the input. This solution to LeetCode problem number 1945, sum of digits of string after convert, is implemented in Python. Let's break it down step by step. 1. Converting letters to numeric positions. The first step is to map each letter in the input string S to its corresponding position in the alphabet, A equals 1, B equals 2, Z equals 26. This is achieved using a generator expression inside join. For each character in the string, we compute its position as char, A, plus 1. The results are concatenated into a single string called numeric_string. 2. Summing the digits repeatedly. After obtaining the numeric string, we repeatedly sum its digits for k iterations. This is done using a for loop. In each iteration, we calculate the sum of the digits of the current numeric_string. The digits are extracted using a generator expression that converts each character in the string to an integer. The result is then converted back to a string to be used in the next iteration. 3. Returning the final result. After k iterations, the value of numeric_string represents the final result, which is returned as an integer. ###efficiency. This approach is efficient with a time complexity approximately proportional to the length of the string S and the number of iterations k. The conversion of letters to their numeric positions takes O(n), where n is the length of S. Each iteration of summing digits involves processing all digits in numeric_string, whose length depends on S. ###edge cases. If S contains only one letter, the algorithm still works as it calculates the numeric position of that single letter. If k is 1, the digits are summed only once, and the loop executes a single iteration. The solution handles any valid lowercase English input string. This is the Java implementation of LeetCode problem number 1945, sum of digits of string after convert. The logic mirrors the Python solution, converting the string to a numeric representation based on letter positions, then performing digit summation iteratively for k times. Key differences include Java's explicit type declarations and use of string builder for string manipulations. To solve this problem, we start by converting the letters in the input string into their corresponding numeric values based on their positions in the alphabet. For the string LeetCode, each letter maps as follows: L becomes 12, E becomes 5, E again becomes 5, T becomes 20, C becomes 3, O becomes 15, D becomes 4, and E becomes 5. By concatenating all these values together, we form the numeric string 1255, 203, 1545. Next, we repeatedly sum the digits of this numeric string a total of k times. In the first iteration, when k equals 1, we calculate the sum of the digits in 1255, 203, 1545, which is 1 plus 2 plus 5 plus 5 plus 2 plus 0 plus 3 plus 1 plus 5 plus 4 plus 5. This equals 33, so now the numeric string is updated to 33. In the second iteration, when k equals 2, we sum the digits of 33, which gives 3 plus 3, resulting in 6. Thus, the numeric string becomes 6 at the end of 2 iterations. In the second example, we follow the same process with the input strings backs and k equal to 1. First, we convert each letter to its numeric value. Z corresponds to 26, B to 2, A to 1, and X to 24. Concatenating these values gives us the numeric string 262124. Since k is 1, we only perform one iteration of summing the digits. Adding the digits in 262124, we calculate 2 plus 6 plus 2 plus 1 plus 2 plus 4, which equals 17. At this point, the numeric string is updated to 17. Since we have completed the single iteration required by k, the final output for this example is 17. In the third example, the input string is I, and we set k to 3. First, we map each I to its numeric value, which is 9. Since the string consists entirely of i's, the numeric string becomes 9999 after concatenation. Next, we sum the digits k times. In the first iteration, when k equals 1, we sum the digits of 9999, which is 9 plus 9 plus 9 plus 9, resulting in 36. This updates the numeric string to 36. In the second iteration, with the updated numeric string 36, we sum the digits again. 3 plus 6 equals 9. This updates the numeric string to 9. Finally, in the third iteration, since the numeric string is already 9, summing its digits simply results in 9. Therefore, the final output for this example is 9. To understand the time complexity of this solution, let's break it into two major steps. First, we convert the input string s into a numeric string. For each character in s, we calculate its position in the alphabet using the formula ord, char, ord, a, plus 1. Since this operation is performed for all n characters in the string, the time complexity for this step is O, n. Next, we repeatedly sum the digits of the numeric string for k iterations. After the conversion, the length of the numeric string can be up to 2 n because each character maps to a number with at most 2 digits, such as the letter Z mapping to 26. In each iteration, we compute the sum of the numeric string's digits. The time required to sum these digits depends on the string's length, which we'll call m. Since this summation occurs k times, the cost of this part is O, k asterisk m. Now let's analyze how the length of the numeric string impacts the summation step. With each iteration, the numeric string shrinks because summing its digits reduces its length. For instance, the sum of digits in a 2-digit number like 26 results in a single-digit number, 8. This means the numeric string stabilizes at a constant length, typically 1 to 2 digits, after a few iterations. Therefore, the total cost of summing digits is mostly influenced by the early iterations, where the string length is proportional to O, n. Combining both steps, we have O, n, for the initial conversion and O, k asterisk n, for digit summation during the iterations. Since the summation step dominates over time, the final time complexity of the solution is O, k asterisk n. Next, let's evaluate the space complexity. The primary space usage comes from storing the numeric string. After converting the input string, the numeric string's maximum length is proportional to 2 n, since each character contributes a 1 or 2-digit number. This simplifies to O, n. During the summation process, we use temporary variables to calculate the sum of digits. These variables require constant space, which is O, 1. Additionally, the solution does not rely on any auxiliary data structures, so the total auxiliary space remains constant at O, 1. Therefore, the overall space complexity is dominated by the numeric string storage, which is O, n. Let's compare this optimized approach with a brute force method. A naive solution might involve repeatedly converting characters to numbers or summing digits inefficiently, resulting in unnecessary recalculations and higher computational overhead. In contrast, this approach minimizes redundant operations by converting the string only once and efficiently summing digits using a single numeric string to track intermediate results. The time complexity of O(k*(n) applies consistently across all cases, as the length of the numeric string is directly proportional to n, and there's no variability in input that would lead to better or worse performance. In conclusion, the time complexity of the solution is O(k*(n), while the space complexity is O(n). This makes the approach efficient and scalable for typical problem constraints, with linear growth relative to the input size and the number of iterations. Let's explore some common mistakes that can occur while solving this problem. First, incorrect letter-to-position mapping is a frequent issue. This happens when you use ORD, char, ORD, which maps the letter A to 0 instead of 1. This off by 1 error can be fixed by adding 1 to the result, so the correct formula becomes ORD, char, ORD, plus 1. Next, ignoring edge cases is another common pitfall. For instance, assuming the string is always non-empty or contains only valid lowercase letters can lead to runtime errors if unexpected inputs occur, like an empty string or invalid characters. To avoid this, it's important to validate the input and handle these cases safely. Lastly, inefficient string traversal, such as using nested loops or performing excessive string operations, can unnecessarily increase the time complexity. The optimal approach is to traverse the string just once and compute the result directly for an O(n) solution. Another mistake is confusing the output format. Some might return the list of numbers as a string instead of a sequence of integers. This typically happens when the problem requirements are misunderstood, leading to outputs like concatenated numbers instead of the expected integer list. The fix here is straightforward: carefully read and follow the output specifications to ensure the format is correct. Overcomplicating the logic is another trap to avoid. For example, using complex data structures like dictionaries for a simple mapping task only adds unnecessary verbosity to your code. Instead, a simple formula like ORD, char, ORD, plus 1 achieves the same result in a cleaner and more efficient manner. Prioritizing simplicity not only improves readability but also makes your code easier to debug and maintain. From an interview perspective, this problem is a great way to test your ability to recognize patterns and apply basic mathematical operations. Understanding how ASCII values relate to character positions is fundamental here. Additionally, strong edge case handling is something interviewers will look for. Be prepared to explain how your solution deals with scenarios like empty strings, non-alphabetic characters, or extremely large inputs. It's worth noting that while this task naturally has an O(n) complexity, interviewers often value clean and readable code over unnecessarily complicated optimizations. Lastly, this problem shares similarities with other LeetCode challenges that you might find useful to practice. For example, problem 804, unique Morse code words, involves mapping transformations, while problem 482, license key formatting, focuses on string manipulation. These related problems can help reinforce the techniques used here. There are also alternative approaches you might consider. One option is to use pre-computed mappings. For example, you could create a dictionary or a list containing the letter-to-position mappings ahead of time. This reduces computation within the loop but comes at the cost of slightly higher memory usage. Another approach, particularly in Python, is to use list comprehension to perform the entire computation in a single concise line of code, such as ORD, C, ORD, plus 1 for C and S. While this is elegant and compact, it can be harder to debug if issues arise. If you're working in Java, a string builder is a great tool to optimize for memory when handling repeated string concatenations. While Python's immutable strings make this unnecessary, it's a useful optimization for other languages. Ultimately, the best approach depends on the language you're using and the specific requirements of the problem. Great work! To summarize, this problem focused on string manipulation, digit summation, and iterative transformations. We covered an efficient solution with O(n) time complexity. Remember, problems like this reinforce fundamental skills that are invaluable for interviews. Thank you for watching, and don't forget to subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!